Hello, welcome to today's lesson where we will be learning about one of the greatest minds in science, Isaac Newton. Specifically, we will begin by learning about Isaac Newton's pivotal role in revolutionizing our understanding of motion and forces. We will explore how, in the late 17th century, Newton formulated three fundamental laws of motion that laid the groundwork for classical mechanics. Finally, we will understand how Newton's laws provide a framework to describe how forces affect the motion of objects, from the falling of an apple to the orbits of planets. So far, we have explored the basics of forces and how they interact with objects. We discussed how forces can change the motion of an object and the different types of forces such as gravity, friction, and tension. Building on this foundation, we can now look at Newton's laws of motion. This lesson will enhance our understanding of how these fundamental laws govern the behavior of objects under the influence of forces. Let's get started. Isaac Newton, born in 1643, played a fundamental role in laying the foundations of classical mechanics. His work in the late 17th century revolutionized our understanding of how forces interact with matter. Among his many contributions, his formulation of the three laws of motion stands out as a cornerstone in the study of physics. Newton's first law, often referred to as the law of inertia, states that an object will remain at rest or in uniform motion in a straight line unless acted upon by a force. This law helps us understand that the natural state of an object is to resist changes in its motion. For instance, a book on a table will remain there until someone applies a force to move it. Newton's second law provides a quantifiable explanation of how forces influence motion. It can be articulated as F equals ma, where F is the force applied to an object, m is the object's mass, and a is the acceleration produced. Essentially, this law tells us that the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. Imagine pushing two objects, a heavy one and a light one, with the same force. The lighter object will accelerate more due to its smaller mass. Newton's third law is commonly phrased as, for every action, there is an equal and opposite reaction. This law introduces the concept of force pairs. If you push against a wall, the wall pushes back with equal force in the opposite direction. It's a crucial principle for understanding interactions, such as why rockets can propel themselves in space. These laws are not just theoretical constructs, they apply to a wide range of phenomena in the natural world. For example, Newton's first law explains why seatbelts are essential in cars. When a car suddenly stops, the passengers tend to keep moving forward due to inertia. Seatbelts provide the necessary force to counteract this motion, keeping passengers safely in place. Newton's second law is fundamental in understanding why different vehicles accelerate differently. A sports car can achieve higher acceleration than a lorry because it has less mass, assuming the same amount of force is applied in both cases. Newton's third law is evident in activities such as swimming or rowing. When a swimmer pushes water backwards with their hands, the water pushes them forwards with equal force, propelling them through the pool. These principles are the bedrock of further exploration in physics, giving us a robust framework to understand how forces affect motion in everyday life and in the vast expanse of the universe. In today's lesson, we delved into the significance of Newton's contributions to physics, specifically his three laws of motion. Understanding these laws equips us with a fundamental framework to describe and predict the behavior of objects under various forces, providing deeper insights into both everyday phenomena and complex systems in the universe. This foundational knowledge in classical mechanics is essential for progressing further in the study of physics. Watch the rest of the GCSE physics course at Sophos Education.